Good evening to all. Let us start today's interactive session. Today we will be discussing about the contents that was discussed in week 11 of the courses Foundation Engineering by the NPTEL, and the course instructor is Professor Kousik Deb from IIT Kharagpur, and I am Kashyap Vasudevan. I'm one of the TAs for this course, and my fellow TA is Mr. Shivjankar Nanti. Okay, so as usual, let us begin with a recap about the previous week. In the previous week, the the week began by an example problem, which was on cantilever retaining wall, based on Rankine's theory. So in the last week, if you recollect, we had slightly mentioned about Rankine's theory. We were solving by Coulomb's theory, but Rankine's theory is also possible to do in certain cases. So one of the problems was solved on based on that. Uh, and after that, certain topics were discussed briefly. For example, releasing water pressure in the backfill. So in all the retaining structures, when water table rises, especially in monsoon in the backfill, we have to release it. We have to provide certain ways for the water to drain out of the backfill. This reduces the lateral pressure, as well as the complications that comes with the shear strength reduces, and the water tends to escape. So one of the ways to two of the ways to release the water pressure from the backfill is by weep hole and perforated pipes. Weep hole is nothing but we are giving a hole on the retaining wall, whether it is retaining wall or any retaining structure, and the water is allowed to escape through it from the backfill directly from the face of the wall. When it comes to perforated pipes, we are laying the perforated pipes which has holes on its on its boundary, and water gets collected in this drainage pipes, and these pipes are connected outside the structure so that it drains out of the backfill. So that is also possible. So whenever we are dealing with coarse grained soil, we need not worry about much. But when it comes to fine grained soil, we are supposed to provide some filter or some graded coarse grained material near the weep hole and perforated pipes, so that there is no blockage, or there is no loss of soil from the backfill, or any piping and all that should not occur. So to avoid erosion in such cases, we are supposed to provide filters and other precautions, so that backfill soil does not erodes away. And after that, we discussed about shear keys. So shear keys is given when sliding resistance is insufficient. So when in the last class we discussed about the stability of a retaining wall. So in the stability of retaining wall, one of the checks was sliding resistance against sliding. So in that case, if I remember properly, in my session, I had discussed a problem where this particular criteria was not satisfied. So in such cases, we can do several things. We can improve the soil in the subgrade. We can so that the delta value increases, or we can also give a shear key. A shear key is nothing but if we have a retaining wall like this in this format. So if we have a backfill like this, what we do is we provide a extra member in the downward direction from the stem, as an extension of the stem, and such that there is a extra the protrusion below the base slab. So now the idea is like, if we have this pressure distribution diagram, what is it, since this is moving, we are the critical condition we are assuming is like the retaining wall is moving away from the backfill. The soil in the near the toe of the toe of the retaining wall provides a passive pressure, passive earth pressure. So we all know that it is quite a higher value than active earth pressure. So within such a lower depth also we get a very high value, provided it is mobilized. So what happens is at this depth, if you are giving shear key, this extra passive earth pressure will help it to resist the retaining wall from sliding. So that is the idea. So at this depth till so this will be acting, the shaded region will be acting, uh, sorry, so this will be pp, the shaded region will be acting on this particular face, that will act as our resisting moment. So in our factor of safety in the numerator, this component will get added so that our factor of safety increases. Okay, so after that we moved on to sheet piles. So the relevance of sheet pile is quite important when it comes to constructions. So sheet pile is very easy to drive to the ground. So that is that's why it is used generally for temporary purposes as well as permanent also. Uh, it's extensively used in places with high water table and also waterlogged areas. The idea is we can drive it through the soil very easily, and assembling is also very easy. uh, what the idea is, like, it is driven through the soil, inside the soil, so that we get a resistance from both the sides, and one will have a extra height whichever backfill is, which will be acting, giving up active earth pressure, and the other side with the passive earth pressure. So the design of sheet pile involves how much depth we are supposed to drive the sheet pile. So that embedment depth is the generally the design factor. Okay, so there are generally two kinds of cantilever, sorry, sheet pile walls. One is cantilever. So when I say cantilever, it's nothing but we have a backfill and we have a sheet pile just like this, sheet pile wall. So it acts as a cantilever, and when sometimes whenever we calculate the embedment depth, it might come out to be a very huge value whenever we have a huge active earth pressure. So in that case, we can provide an extra member that is called the anchor. So what we do is we anchor our sheet pile inside our backfill, so that we get an extra resistance from the uh, backfill. So what this helps us to give a smaller dimension of the sheet pile, and the cross section, the requirement, the material requirement will be much lesser. So the efficiency of this member increases. So this is also used in such cases. That is, uh, there are sometimes even multiple anchors are given at different depths. So these are the two different sheet pile walls. After that, we moved on to analysis of cantilever sheet pile walls, the first type of walls for granular soils. So for granular soils, C is equal to 0 condition, analysis of sheet pile was explained in detail, and one example problem was also solved in the class. So in this particular session, we will be solving one of them, one solution, one cantilever sheet pile was in the soil. And towards the end of the session, he started our instructor started solving analysis of cantilever sheet pile walls in purely cohesive soil. So in this case, our angle of internal friction will be 0. So having said that, let us move on to the for today's problems. Now the first problem is quite simple. Uh, so the idea is we are supposed to find the head. So the question is that we have a retaining wall embedded as shown below. If the embedment depth is determined using approximate method, find out what would be the height of the backfill. So we are supposed to find, so this is the embedment depth, that is d. We are supposed to find h, that is the height of the backfill. So uh, we have the properties here. So we need both coefficient of active earth pressure as well as passive earth pressure. So let us jump on to this and just find out that value before solving it. So we all know that active earth pressure coefficient can be written as 1 minus sine phi by 1 plus sine phi. So phi value is 40 here. So sine 40 by 1 plus sine 40. This value is mm, this value is 0.2127. And when it comes to passive earth pressure, I can write it as 1 plus sine phi by 1 minus sine phi. Also, it's nothing but 1 by Ka. This is nothing but 4.599. Okay. Okay. So when we have a sheet pile, when we have to analyze a sheet pile, especially for a cohesionless soil, um, we have actually two options. Uh, One option is this approximate method that we are talking about this in this question. There in this method, what we are trying to do is we are assuming that our sheet pile is deforming angular in an angular way uh, about our base. So about our base, this so the first approximate method, we are assuming that the sheet pile wall is getting deformed about the base. So the pivot is at the base. So we can take the that's why we are assuming the whole right hand side, the backfill side, is contributing for active earth pressure completely, and the other side will be resisting the movement. It will give a passive earth pressure. So this is a very simplistic approach, which may not be true, because the assumption that it deforms about the base, it may not be true. So this is a very simplistic approach. That's why it's called an approximate method. We can this we can solve it in a very small amount of time. So it's very less complex. So here our thing will be straightforward. It will be like Ka gamma d plus h, and here it will be Kp gamma d. So it's as simple as that. So we have a resistance here, and we have a PA and TP. That's all. So passive case and active case. But when it comes to sorry, this is not approximate. This is exact, accurate. So accurate analysis is when we have a pivot. So if we have a pivot, we will let us assume that it will deform about the pivot. So below the pivot, let us say O, it will be a passive. So this backfill side will be providing from left to right. So from right to left, it will be providing a passive pressure. So below this depth, it will be. So we can actually divide it into different zones. 1, 2, 3, 4. So this will be passive, this will be active, and this will be active, and this will be passive. So we can judge that from the movement of the sheet pile towards or away from the soil. If it is towards the soil, it is passive. So that is the idea. So that is more exact and complex. So that will is it not be generally asked for a small question. So we can solve it. So it's here PA will be involved, and we will have to extend this, and we have to get the PP1 and PP2. We will see that later. So that is more complex to analyze, and so in this particular question, we are supposed to deal with approximate method, whatever we showed it here in as well. Okay. So having said that, let us start. So here we have df is equal to df is given. We don't know h. That is what we are supposed to find out, and we know that our Ka is equal to 0.217, and Kp is equal to 4.599, and what else? Gamma is equal to 20 kilonewton per meter cube. Okay. So as we told before, our this base will be Kp gamma df, and this base at this base it will be Ka gamma df plus h. So we need not worry about anything, since we know this is the pivot, and if let us say this as B, we can take our moment about B, it should be 0, right? So moment about taking moment about b is equal to 0, we can directly solve this. So let me say like in the LHS, in the right side, this is the passive and this is the active. So passive side I can write it as, I can write the area of the whole triangle as k half into kp gamma df, that is a base, into height of this is df, into a distance. So this distance is nothing but df by 3, and this distance is nothing but df plus h by 3. So into this will be df by 3. So moment of clockwise moment because of the passive earth pressure is written. Anti-clockwise moment about because of active earth pressure can be written as half into ka gamma df plus h, that is our base, into height df plus h, into distance, that is df plus h by 3. So this should be equal to 0. So we have the moment equal to 0. So I can equate the both and write it as uh, I can write half into kp gamma df cubed by 3 is equal to half into ka gamma df plus h cubed by 3. So I can, here only I can cancel a few things. I can cancel my half on both sides and gamma on both sides. So actually it's not depending on our density at all. So we have I think I can also cancel 3 and 3. Now we know that df is 4, so I can substitute that, and let me see. So if I substitute df is 4, kp 4 cube is equal to ka 4 plus h cube. We know kp and ka, and if we substitute that, we can directly arrive at h. So sometimes h may not be given, we will have to arrive at embeddment with df. So in whichever case we can solve this. So so this will be 4.599 and into 4 cube, and this will be equal to 0.217 into 4 plus h whole cube. So if you solve this, we can solve for h. H will be is equal to 7.07. So we have one of the options as 7.07, that is 7.1. That will be the answer. So this is very simplistic. As I told you, this will be the go-to method for generally for even in your assignment. I guess we have a similar problem, and uh, just taking the basic moment at the base at the b this point is enough for solving this. Okay, moving on to the second question. In the second question, it is asked, we are supposed to find the cantilever sheet pile. We have on a portionless soil. The height is 6 meter, and the water table is at 2 meter below. And calculate a dash, the point of a dash between the dredge line and the point of zero pressure just below the dredge line. Okay. So before we jump onto the question, uh, this is my h value, h is equal to 6, and this is my df we don't know, and water table we have water table at 2 meter depth, and we are supposed to find a dash. So I hope you have gone through the last week material. So in that a dash and those things are directly given. Before that, let us just uh, okay, I think there is a mistake here. This is not 40, this is 35 degrees. Okay, so here let us see what will be the first. Let us just solve this k and kp, so that we need, anyway we need it in future. So 1 minus sine 5 sine 35 divided by 1 plus sine 35. So if we solve this, we will get 0.271, and kp will be 1 plus sine 35 by 1 minus sine 35. This will be 3.69. So we have ky and kp. Now what we do is we need to analyze it. So here this is not approximate method. We are going for the accurate exact method. Accurate in the accurate method, here we are not told to find the embedment depth directly. We are just told to find the distance of A, that is between the dredge line and point of zero pressure. We are supposed to find the distance. So what they are trying to say is, so let us say this is our H and this is our DF, and we have the water table. We have water table here at 2 meter. So this is 4 meter. Our A dash is nothing but this value. That is distance. A dash is a distance between the dredge line and the point of zero pressure. So this is the dredge line and this is the line of zero pressure. So this is our A dash. We are supposed to find A dash. Okay. Now what else do we need? For this we need one value. We need the pressure at this. So let this be the pressure PA. So small letter PA. So we have an equation for PA. We can find PA easily. So let us say this one. This one is PB. Okay. So how to solve for that? We can write P B is equal to, so this PB is nothing but our gamma. Okay, so our gamma above is 18 kilonewton per meter cube. I forgot to mention that. This is 18 kilonewton, saturated is 18 kilonewton per meter cube, and this is bulk also 18 kilonewton per meter cube. So my submerged is nothing but 8 kilonewton per meter. So I'll write gamma dash here as 8 kilonewton per meter cube. Okay. So here my lateral pressure at this depth, that is 2 meter depth, is Ka gamma 2, right? So that I can write it as Ka is 0.271 into gamma is 18, the 2 is 9.756 kilonewton per meter square. So this is the pressure at A. So at A, so if I write PA, that is at this depth, that is a dredge level. At dredge level, if I want to find out, it will be basically this PB, that is this value, plus our depth in the submerged region. So the first term will be the same as before, PB, that is the first 2 meter. In the next 4 meters, we have submerged unit weight. So I have to write it as Ka, that is 271 into 4 meters into 8. 8 is the density, the submerged density. This turns out to be 18.428 kP. So we have the pressures, that is 9.756 kPa and 18.428 kPa. Okay. So in order to find A dash, we have the equation A dash is equal to PA by Ka minus Kp into gamma dash. So this will be PA is nothing but 18.428 divided by Ka minus Kp gamma dash. Okay, I could have substituted it. So Ka is equal to 0.271. Sorry, it's actually Kp minus Ka. Kp minus Ka. So that is 3.69 minus 0.271 into gamma dash. Gamma dash is 8. So this turns out to be 0.67. So that is our answer that we require here. A dash which is asked, that is 0.6. Okay, so this is just one small step in the actual design of the retaining, sorry, the sheet pile wall, cantilever sheet pile wall. But the question, are generally is, simple questions are asked whether it is assignment or the exam. So uh, this is as simple as that. So this is this equation that I was talking about. I'll write it in a better way. Kp minus Ka into gamma dash. Gamma dash in the sense whichever is the density at that level, that is the A dash level, we have to take that. Okay. So having said that, let's move on to the next question, which is nothing but the continuation of the first one. In this, what we'll do is, what is asked is we are supposed to find the distance between the point of zero as well as the point of application of our pressure. So we have this much. In this much area, we'll have a pressure, that is PA, total pressure. So here we know it is 9.756 kPa, and here we know it is 18.428 kPa. So from this figure, I can arrive at a pressure. So if I divide, for example, if I divide this as 1, 2, 3, and 4, I can add the all the areas and I'll get the PA. So, but what is asked is we are supposed to find the distance between point of zero, that is our this line. This is where it is zero. So zero pressure, and point of application of our total load, that is our this load. So this I can name it as y bar. So what I'll do is I'll find the each forces, and I'll check the moment about this point at the zero pressure point, and that at that point, if I find the I can find the position of our total load. It's that simple. So let us just continue solving. So I can write our total. So each figure I'm going to write as 4 terms. So my total load, that is PA, I'm going to write it as 4 terms, that is P1 plus P2 plus P3 plus P4, assuming that each of these are P1. So this is P2, this is P3, and this is P4. Taking that, I can write it as, first one is nothing but half into base is 9.756 into height is 2 meter. So second one is half, not sorry, half, it will be the rectangular part. So the rectangular part is nothing but 9.756 into height is 4 meter. uh, Height is 4 meter. And in the next third term is this triangle, so the triangle 3. So here I have half into base is nothing but my 18.428 minus 9.756 into height is 4 meter, and my third term is this triangle, this inverted triangle. So sorry, my fourth one is that inverted triangle, that is half into base is 18.428 into height is my A dash. So A dash is nothing but 0.067, that we already know. So this is A dash is equal to 0.67 meter. So I can write half into base into 0.6. So now if I solve this, I'll get P1 as same thing, 9.56, and P2 as 339.024, and P3 as 17.344, and P4 as 6.10. So if I add everything, I'll get the total as 72.297. So this is my total pressure. So my total force is 72.297 kilometer. So I have the total force. I can find the different the the different position of these. So the position of each force I'm going to write. So for the first force, the position is from the this point. So from this point, I want the position. That is y1 is equal to 0.67. That is our a dash plus 4 meter plus 2 by 3. That is 5.3367. My y2 is 0.67 plus 4 by 2. That is 2.67. Okay. That is equal to 2.67 meter. So I am talking about this particular thing. So from 0.67, oh sorry. So 0.67, excuse me. Okay. Uh, so when we say the next one, so y3, next figure is y3, that is this triangle. That triangle is 0.67 plus 4 by 3, right? So that is 0.67 plus 4 by 3. That will be 2 meter, and y4 will be just 2 by 3 of this height. So 2 by 3 into 0.67, that is 0.4467. So we have all the heights of each forces. Now we can arrive at our required, that the height of the position of our total force, that is 9.756 into 5.33. Okay, just for understanding, I can write it as P1 y1 plus P2 y2 plus P3 y3 plus P4 y4 divided by P1 plus P2 plus P3 plus P4, right? So I can write it as 9.756 into 5.337 plus 39.024 into 2.67 plus 17.344 into 2 plus 6.17 into 0.45. So if I divide the whole by the total, our total is 72.297. We get y dash is equal to 2.68. Okay. So y dash, that is, this is equal to 2.68 meter. So that is our answer. So one of the option is 2.68. So that is what is asked. So in our exams and assignments, the problems will be like this. It will be very basic and simple. Uh, but for the completion of this particular problem, I would like to solve it to find out the depth of our embedment. So embedment depth we can arrive using the. So similar problem was solved in the class, in the session, and one of the videos also, the last week also. So we will proceed with the same problem to arrive at the embedment depth. So in this design, for generally for the design of sheet piles, our embedment depth, the df is the factor. So let us do that. So okay. So when I say this exact or this accurate method, we have to understand a few more things. So till now we talked about our dredge level. So if if this is the uh, backfill and sheet pile, this is a dash. A dash we know, that is already we took it as 0.67 meter, and we have a force, that is PA, that is 72.297, and we have y bar. Y bar is nothing but this distance, we have that as 2.68 meter, and we are going to bring some more name like terms. One of them is this distance. Okay, so we'll write it in a better way. So this can be taken as capital Y. So let us say this is capital Y and this is my df. I can write df is equal to capital Y plus a dash, which is quite evident from the diagram. And this is my h. So I know that h is equal to 6 meter and this is 2 meter and this is 4 meter. We all know that. Okay, so I'm going to name these each point. So A, Z, so O, the pivot is O, and let this be C dash, B, and C. So this particular distance, the pivot to the bottom, let us say that is a capital Z. So this particular distance, that is PP1 and PP dash, PP2. So there are two stresses, PP1 and PP2. Sorry, PP1 and PP2. So here there are formulas to arrive at this. It's simple. So what we are trying to say is this is the base. So here if you are extending this line from the trench level to the base, we'll get this PP2, and if you are extending this particular thing, that is PP1. So the explanation why the shape is like that and those things are in detail explained in the third video, I guess. So in that, this PP1 and PP2 is explained. So what we are trying to do is if we follow this if we try to derive this PP1 and PP2, PP1 is nothing but Kp gamma h plus d minus Ka gamma t. So here uh, this is like I can also simplify this as Kp minus Ka into gamma y plus Kp minus Ka into gamma a dash plus Kp gamma h. So if you simplify, if you split this df, that is our embedment depth, into y, capital Y and a dash, we can arrive at this particular this thing. So geometrically also you can prove this. It's already shown in the video, so I'm not spending time on that. So this is it. So this is pp1. So pp1 I can okay, so I'll write the pp2 expression. So pp2 is written as pp2 can be written as kp minus ka into gamma y. Okay, so these are the two expressions here. So let us just find out and see what happens. pp1 is equal to kp, I know that is 3.69 minus ka is 0.271, and gamma, so here this gamma we are talking about y. So y is below this water table, so we are supposed to take submerged one. So that is 8 into y plus 3.69 minus 0.271 gamma, again 8, a dash is below the water table, and a dash we know it as 0.67 plus 3.69, that is our kp, into gamma. So here gamma h. So h, when I say h, we have both above water table and below water table. So I'm going to split it accordingly. That is 18 into 2, that is the top 2 meter, plus 8 into 4, that is the remaining 4 meters of h. So we are supposed to take those density in such a way that, because this is our, sorry, because This is nothing but this is a weighted density. So accordingly, so depending on the uh, so I should not say weighted density, I should say depending on this height, the height of this, wherever our position is, we have to this value we will have to adjust. So gamma 1 h1 plus gamma 2 h2, like that we'll have to add it up. So that's what we are doing here. uh, so pp1, so I can solve this and I can arrive at a value that pp1 is equal to, I can write it as 27.35 y plus 269.25. So here uh, we have pp1 in terms of y. Y is an unknown, we don't know yet. That is the whole idea. Y is the thing that we are trying to find out. And pp2 I can write it as kp minus sorry uh, that is 3.69 kp minus ka 3.69 minus ka is 0.271 into gamma y. Gamma is nothing but 8 into y. So this turns out to be 27.35 y. So I have pp2 as 27.35 y. So see, now we have an equation for pp1 and pp2 in terms of y. Okay, now the thing is like we can solve. So pp2 we have, pp1 we have in terms of y, pa also we know. So what we are trying to do is we can find the only these portions. So there is no problem with respect to pa because we already know the values and the position. But when it comes to the bottom, so below the a, below this a point, we what we do is we will subtract, in order to get the other two figures. I can subtract a c dash c, that is a triangle a c dash c minus triangle z c dash c, sorry, a c dash b minus z c dash c. If we do that, we will get a direction in terms of the other direction. So the force, in order to get the shade at this region, we have to do this. We can divide it into two triangles and we can subtract. So if we do that, we can get this particular area. So once we get that area, we will get the force. So the idea is to make this in equilibrium. So we have two equations for equilibrium, that is sigma Fh, that is the horizontal forces, should be equal to 0, and sigma Mb, that is about the base or whichever point we can take, moment about that particular point should be 0. A, or you can also take at the base B, whichever you feel like. So the idea is we are supposed to use these triangles separately and in the opposite sign, so that it gets cancelled and we get this a shaded area. So if you do these two, I'm not going to in detail because it will take a lot of time. If you do these two, that is if you solve these two for the shaded areas, we will get the following formula, that is 6 pa, that is our total force, into y plus y bar plus z square pp1 plus pp2 minus pp2 y square. So here this particular equation, we need not remember this, but uh, this is the equation that you get if you use these two equations. So now we don't know what is z. So z is equal to pp2 y minus 2pa divided by pp1 plus pp2. This you will get easily from sigma, this fh equal to 0. So the z is nothing but this particular distance, this distance that is from the pivot to the base, that is our z. So using that we can define z. So if you want to further simplify this, we can substitute this z in our in this equation, that is this, let this be 3, equation 3. We can substitute that and we'll get as 6pa y plus y bar plus pp2 y minus 2pa divided by this will be whole square divided by pp1 plus pp2 minus pp2 y square. So this equation is quite overwhelming, but uh, this is how to do this exact method. So this is my fourth. So I can substitute all the values now. This is equated to 0. I can substitute all my values with respect to y. So I have PA, that is an exact value. PP1 and PP2 are in terms of y, in the terms of y, and y bar also I know. So if I substitute everything, let us see what happens. So if I substitute everything in the previous equation, my PA, capital PA is 72.9297, and y plus y bar is 2.68, we just solved before, plus in the numerator we have a pp2, that is sorry, pp2, that is where pp2 is nothing but 27.37y plus 2 point into y. So pp, sorry, so in the equation we have pp2y. So my pp2 is 27.35y into y minus 2 into pa. Pa is nothing but 72.9297. So this whole square divided by pp1, that is 27 plus 35y plus 29, sorry, 269.25. This is the whole pp1 plus pp2, that is 27.35. Sorry, okay. So this is the second term. The third term is minus pp2 y square. So minus pp2, that is 27.35 y square. Okay, so this is the equation. Everything is in terms of y now. So after, if we spend a certain time, like enough time, we can solve this with respect to y. So what happens is, like, if I solve this, I will be arriving upon on simplification. This equation will be 748.03 y4 minus 736,399 y cube plus 15818.7 y square plus 1803, the numbers are quite big, 66y plus 333,919.27. This will be equal to 0. So this is our equation after simplification. So it is a quartic equation, that is the polynomial equation with the degree with the power of 4. So this is a quartic equation. So how to solve this quartic equation is quite hectic, but there are different mathematical tools. Even in some calculators we can do this, or we in internet we can do this. But if at all we don't have any calculator, we can also do by trial and error. When you are doing trial and error, we can begin with y is equal to h around whichever value. For example, we can also here begin with uh, uh, our h is 6 meters, so we can start with 6. So if you substitute 6, y as 6, you'll get some value, so that depending on that we can keep on changing, trial and error. We can arrive at the answer. So the y value to obtain right. So one value will give a positive answer, positive inequality, and if you give next at 6 7 5 5, you can get another. So depending on wherever it's converging, we can arrive at a, maybe in 5 or 6 attempts we can come up with some answer. So that is a hectic method. Also, if you have any tools, I used a mathematical tool online for solving this quadratic equation, and you will get the answer as 5.365. So our y value is 5.365. So if our y is that, as we told before, df is nothing but a dash plus y. From the figure, that is quite clear. So 0.67 plus 5.365, that is 6.035. So our height of the backfill itself is 6 meter, and embedment depth, according to the exact this thing is also 6 meter. So generally, when we have this thing, we are supposed to provide D provided at 30% extra. So we are supposed to increase this particular length by 30% for safety, because the passive pressure may not be mobilized as we expect. So 7.8, this will be 7.85 meter. That is almost 8 meter. We can provide a distance of 8 meter, but this 8 meter is quite high. This value is quite high because our if this is our embed our sheet pile, this was 6 meter, and now this is 8 meter, which is quite high. It doesn't make much sense. So lot of material is also waste. In such cases, when we have such a value, we can go for, since d is d is very high, we may provide anchor. So anchors is nothing but the same thing. I can do it as, so this is 6 meter. We can provide an anchor within the backfill, and that will provide some resistance. So so that our lateral pressures are reduced and resisted properly. So that comes under anchored sheet piles. So that will be dealt in the next week. And also, these all things were for cohesionless soil. So sir started to explain about analysis of sheet pile, cantilever sheet piles for cohesive soil this last week, and in the last video. So we'll be solving more problems on that in the next week. And after that, anchor sheet pile being discussed. That will be done after that. And so that is the purpose of this anchor sheet pile. So this particular question defines that uh, this is the exact method that I was talking about. Okay. Um so yeah, so that's it for today. So here, the exact method, that is a accurate method that I was talking about, is quite complicated. If you have any doubts about it, or like where if anything is missing, that you're finding it not comfortable, you can always share your doubts in discussion forum, or you can also, in between the sessions, you can interrupt. This is the 11th week, and we are moving towards towards the end of the course. The next one will be the last session from our side. And so if you have any doubts, please post in the discussion forum. We'll be meeting in the next week. Uh, So next session is by Mr. Shivshankar Nandi on Saturday, 15th, and I'll be meeting you on 17th. That is the next Monday. So thanks for joining once again. So have a nice day.